I was Cleopatra. I was young and an actress when you knelt by my mattress and asked for my hand. But I was sad.
Hi there. My name is Tanner J. Allen, and I'm a junior engineering major at Cornell College. And a little over 1 week ago, my group and I were tasked with designing an affordable way for home hobbyists, artists, and designers to test 3D printed polymers using a nice compact machine. And as the lead of the design and analysis portion of this project, I want to take some time to go ahead and talk you through the design and exactly why we did what we did and how we did what we did. Looking at our design from afar, one will see that it has the width of 1 foot and the height of 2 feet. This takes up a nice small space that can easily be set on top of a table or sturdy workbench and allow the user to actually see the test happen at eye level. It also allows for the user to easily load weights into the bucket or mass hanger that they will be using in order to apply the load without having to bend over or do any unnecessary lifting from down to the ground. The first thing we started designing was the frame. We had in mind that we wanted this to be a very easily modular assembly. This goes hand in hand with the notion that the hobbyist probably isn't going to be using this from day to day jobs, but rather they're going to take this out at times when they're working on a random project where they're curious about maybe how well this thing tests or something like that. So that is the main reason why we decided to go with the 80/20 aluminum extruded tube, as it can be easily taken down but equally easy to set back up. At the bottom of the frame, you'll see two plastic catch plates. On the occasion a substantial amount of weight is loaded into the bucket and the specimen breaks, these will catch the bucket from falling and potentially hurting the frame or spilling out the weights, which could cause harm to the actual user. The next critical component of our design is the support arm, which is where the force and the load we'll apply to the specimen will be directed down to. It is fastened to the frame to the left and right using a total of 6 screws and nuts. It is made of steel to ensure that the deflection is minimal and it does not impact the calculations the user will be taking from using the machine itself. The support arm features 3 innovative notch designs. The first being a channel which allows for the blue aluminum dowels to be set on top of the support arm while ensuring that they are perfectly centered where the load will be applied from. The second set of notches here are alignment notches. They're featured on both the front and the back of the design and allow for the user to set the specimen onto the dowel pins and align it from left to right at eye level if using it on a table. And allows the specimen to be perfectly centered for the load to be applied in the center and ensure that the actual deformation and the deflection is symmetrical on either side. And the final and arguably most important notch is in the center here. This notch is where the load hanger and the load will be applied to. By having this notch, it constrains the load hanger from the left and the right to ensure the load dowel pin is contacting the specimen in the perfect center and ensuring an equal and symmetrical load on the specimen. Here is a picture of the specimen loaded onto the support arm using the alignment notches to make sure it is aligned laterally from left to right. So here is an image of the actual hanger where we will load dowel pins into these 2 holes. The top one being the one that will come into contact with the specimen, and the bottom one being a hole for a groove dowel pin for a bucket or mass hanger or something of weight to be applied to the actual specimen, so the user can use that in their calculations of how strong the design that they're testing actually is. So here's an image of the assembly where the user will actually test the specimen. As you can see, the load hanger falls in between the support arm using that notch. And then the bucket is also affixed to the bottom of the hanger. Here is a close-up of that assembly to show you exactly how all these components will interface and create the actual test that we desire. So At this point, we had designed a way to apply a force to the specimen, but we had yet to really design a way to actually measure the deflection because this material will be moving as the load is applied. So, in order to ease the calculations for the user, we decided to use a digital dial indicator, which will set on the load hanger and allow it to measure the up and down motion of the actual specimen after load is being applied. We chose a digital dial indicator because users can see the deflection at a quick glance without having to look at needles and understand standard fractions that might be associated with the dial indicator. The dial indicator is set upon a dial indicator case, which will be 3D printed. It is fastened to the frame, hanging on the top, but also a screw at the top constrains this laterally from left to the right. But in the occasion the unit becomes off balance, the user can easily loosen this screw and move the indicator from left to right to gather different measurements if situations were to change.
For our materials testing machine, we used the ASTM D790 testing standards for the flexural properties of unreinforced or reinforced plastics, since we want to test 3D printed polymers. So this testing standard tells us how to use the 3-point bending test to find the flexural stress and flexural strain. And it works best for strains that are within 5%. The test document also tells us specifications for the testing apparatus and how to calculate these values. Following these, we decided that the test supports and the loading nose radii would be 5 millimeters, and it gave us the direction that the support span to the depth or the thickness of the testing specimen should be 16:1. So that set our span at 80 millimeters, and our thickness of the specimen should be 5 millimeters. Lastly, we tried our best to minimize the flex of the overall testing apparatus in order to give the best accuracy for measurements that the user will be taking. Yeah. Here's our materials testing machine frame. To use it, you'll want to have your specimen on hand, as well as some weights in a bucket. First, you'll want to make sure that this support arm, is level to the ground, and you also want to make sure that the indicator case is centered along the top of the support frame. You can adjust those all with these bolts right there. Once those are in place, you can take your test specimen, make sure you measure the width and the depth of it, and then you'll place it on the supports right there and line it up with the grooves on the sides to make sure it's centered. You'll also want to take the weights of the load hanger in your bucket and the dowels, so you can take that into account of your calculations. Once you've got those, you can put those in place on top of the specimen. The hanger will line up with the groove so it stays centered. Then you put the bucket in place like that, and put the last dowel in place right there. There's a little bit of a groove in that dowel also to keep the bucket centered. And then you'll take your load and deflection measurements as you add to your weights until the test specimen breaks, and you'll repeat it at least 5 times, and then you're good.
Our manufacturing process total came to $27.94 and does not include the base cost for each material. The machining cost per hour was based off of the $30 given to us by the prom. Our most expensive piece was our support arm, as it came in at $16 and was created from low carbon steel. Key components in creating the support bar was CNC machine, plasma cutting, and drill press. Our only piece that was created by A 3D printer was the indicator case, and it came in at $1.30. We used 51 centimeters cubed of filament to create a solid infill. The reason behind a solid infill was to create a more durable design. A hanger for the bucket came in at $6.32. The hanger was created from scraps by the support arm, and key components for creating the hanger was plasma cutting, drill press, and welding. Our less manufactured piece was our bucket catcher, as it came in at $1.32 and only consisted of 4 drill pressed holes that connected the sheet to the frame. Our dowel rods was created from a bar that was 11 millimeters in diameter and 1 foot in length, which only consisted of one key component of plasma cutting that came in at $3.
To calculate the flexural stress and the flexural strain of your material, you'll use the load and deflection data that you get from the materials testing, as well as the support span, L, the specimen width, B, and the specimen depth, B, and plug all of that into these two equations. For the flexural stress, you'll want to also take into account the weight of the hanger in the bucket, about half a kilogram, and add that to the load. For the flexural strain, you don't have to take anything into account. As Tanner will show, the support arm doesn't flex that much. We approximated 15.9 kilograms for a load that would make the specimen break. This was from the flexural stress equation, and taking that to be 75 megapascals, which is about an upper limit. For the deflection, we used a flexural strain of 0.5%, which is the range where our materials testing machine works best at. So beyond 10.7 millimeters strain or of deflection, your results will be less accurate.
So, based off of Elizabeth's calculations, we wanted to look more into what's going to happen to the structure if we're going to put the loads that we think we're going to put on, uh, and we want to see how our support is actually going to move and whether or not this is going to affect the deflections that we measure on the specimen. So we started off with the formula that Young's modulus is equal to the stress divided by the strain. And then we isolate the strain, and we want to find the strain of steel. So we approximate sigma load to represent the actual pressure that's going to be placed on the support arm, because we're curious how the support arm is going to move with it being steel and the load that we're going to apply to it. So with the 15.9 kilograms that Elizabeth found will be placed on, we found the area where this load is going to be deflected onto to be around 772 millimeters squared on our actual support arm. So this means the load is going to have a total pressure of about 0.202 megapascals. So then we take into account the Young's modulus of steel, which is around 200 gigapascals. And that's just for a mild steel. So we put this all into calculation, and we find that the strain of the steel that we're actually going to be looking at when we apply this 15.9 kilogram load is around a 10,000th of a percent. So it's very minimal, and we will argue that it's not going to make a big difference in the final deflections of the actual specimen. And this is the only piece that comes into direct contact with the specimen. So we found all other forms of deflection within our structure to be negligible in the calculations of actually extracting the material properties from our assembly and our test design. So we also were very curious about how our structure will hold up in total to an actual load. How much load can we put on this thing? So we found that the weakest point on our structure is going to be the support arm. This is largely due to the fact that it's secured by a frictional fit of a nut within the actual support structure. There's no hard thread that allows for a nice secure connection. Rather, it just largely depends on the coefficient of static friction between the steel nut and then the aluminum extruded tube. So we got to work trying to figure out how much does this actually matter. And we found this equation, which says the torque is equal to the coefficient of static friction times the major diameter of the screw times the clamping force. And by finding the clamping force, we can know how much normal force there is on the nut against the aluminum, which will tell us exactly how much each screw can hold up. So we isolate force and we solve for all the other variables, and we see that the actual clamping force we're going to experience on the nut itself is around 2,030 newtons. However, this is in between the screw and the nut itself, but the nut also comes in contact with the aluminum extruded tube. So because of this, we have to take into account another coefficient of static friction, which is 0.6 for aluminum on steel. So we take this and we find that the total force that we can expect of static friction to keep the screw from moving up and down is the equivalent of 1,240 newtons. However, because this is a consumer product, we want to make sure that we're keeping the actual user of this product safe. So we're going to divide this factor. We're going to divide this number by a factor of 5, and this will ensure a nice padded safety window where the user will not get hurt. We aren't going to expect any like fast fractures or random shearing of the bolt with that. So we found this as a nice figure. And we found that for each screw, once we divide by 5, we're looking around 250 newtons. So the maximum mass per screw we found by dividing by the acceleration of gravity is around 25 kilograms. So every screw can hold up just over 50 pounds of force before it will actually it'll actually fail, but where we feel confident that the user will be safe. So we multiply this times 6 screws, and we see that the total load that our support arm can actually withhold is around 150 kilograms, keeping the user safety in mind. This is the equivalent of around 340 pounds. So while we don't suggest applying this load because you're going to have issues of deflection, we're confident that our structure is strong enough to actually be able to test the materials until they actually were to rupture if the user is interested in doing so.
All right. So I would talk a little bit about our bill of materials for our 3-point testing machine. We were able to come out with a price of about $216.53 for the entire thing, which does meet our goal of a maximum of $300. We included all of our parts in this chart along with a description, price, and a subtotal. So for example, for our silver corner bracket, we talk a little bit about its description, how many we needed, and how much it came out to be. So for most of these parts, we found them on McMaster-Carr, which allows us to not worry about the manufacturing cost and just worry about it by the unit. Another piece that we didn't need to worry about the manufacturing cost is the dial indicator. This is because we would be buying it straight off of Amazon and not need to worry about any construction. There are several parts that do require manufacturing costs, such as our steel bar. This was our support arm for the specimen, and it would need to have holes drilled, and it needed to be cut to fit into our frame. So what we needed to do is cut out holes. It also needed like little areas for the steel rod to rest, so the specimen can rest on those steel rods. So in order to do that, there does need to be a little bit of a manufacturing cost. Also, for the steel rods, they are going to need to be cut from its 1 foot length, because that's the length that it comes from on McMaster-Carr. We need to trim those to its exact length that we need in the support arm. Next, we have one piece that is 3D printed. We decided to do that because it was a cheap and easy way to hold up the indicator, which we were able to come out to about $1.30 based on the material that was used and how much of it was going to be used in general. Also, we threw in the hex L key because all the what's going to be holding it together were hex screws, and this would be a nice and easy way to include that for the user. Nothing too complicated in terms of use and like construction. Also, we decided to throw in the bucket, even though we would expect the user to have one. We decided to include it anyways. Um, that also would have been purchased online or at a store or something like that. So we were able to add that to the total, and yeah. So yeah, we totaled all that up and we're able to come out with $216.53, which is very good for the user and it meets our goal. So now Kale will talk a little bit about future improvements as well as our conclusion.
As a group, we've came to the conclusion that we are proud of our design, that we were able to fulfill the regulations given to us by the ASTM 790, as well as fulfill the budget requirements of $300 given to us. But with every design, it could be better, it could be more efficient. And for future improvements, we want to change the cost of our design, whether it's changing the materials that is used in it or even changing the manufacturing process. That being using a different CNC method or using a cheaper welding or cheaper even plasma cutting. Something that will make it more cost effective, or even changing the design, making it a 4-point test, or making it being able to test a vast variety of materials. But the most important thing, we need to find a way to exclude the weight of the bucket and the hanger, because as it sits now, the weight of the bucket and hanger is included into the equation for deformation, and we want to be able to neglect that. Thank you for your time, and thank you for your consideration.
I was clean with Petra. I was young.